Welcome back to another recording of the VIPER Mainframe Emulation System. Today I want to talk about variables and more memory management and why, once we see the converted code in Python, why is it the way it is. So you can see we have our VS Code up here. So the easiest thing that we can do to get COBOL into Python is to run our Cobra script. So we'll go ahead and run it against this Hello World 3 hierarchical variables. That puts it into the converted directory, as we see over here. Here's our file. Okay, so the first thing that we're going to look at here is the working storage section. Let's keep this open. And let's open up our COBOL file. Keep this open. So here's our list of variables in our working storage section. This is not a COBOL course. I'm not going to necessarily go over, COBOL syntax itself, but I want to talk about the challenges of COBOL syntax and how we're going to deal with it in the Python file. So if you remember from a previous video, I talked about the hierarchical variables and how memory in COBOL is a continuous line of bytes set aside. So during compilation time, we know the bytes that are going to be needed for all the variables in our working storage section, in our linkage section, so how much memory needs to be set aside, and that needs to be a continuous line, because like the whole hello world string we know is 11 bytes long. It starts in position 0. Hello string is 5 bytes long, also starting in position 0, and then hs1 is 3 bytes long, also starting in position 0. So this is position 0 for a length of 3, position 0 for a length of 5, position 0 for a length of 11. How I handle this in the Python world is pretty much the same. I create a memory variable, which is basically a string, for as big as it needs to be for all the variables lined up together. As you can imagine, this could get pretty large. However, on a 64-bit system, a Python string can be, I looked it up, it's like 1 billion bytes or so. I mean, it's something crazy. So hopefully we're not going to be blowing out our system because of poorly written COBOL code that requires strings to be millions and billions of bytes long. And I understand we might be dealing with files that are, millions of records, but hopefully we're not reading in every single record at the same time and trying to store it within memory. Anyway, moving on. So the first thing that I do is I set aside a class or an object instance of a class for the variable itself. So as you can see here, we have the hello world, the hello string, the hs1, we have them all. And we show the length of the variable. So hello world and hello string are length 0. Well, we know that they're length 11 and 5 respectively. Well, that's because since it's not explicitly defined length here, during compilation time, I determined that it was easier during runtime to figure out what that length is going to be rather than at compilation time. Now, is that the right choice? I don't know. But it is the choice I made, so it's what we're going with for right now. So we're going to add all these variables into our variable list. So this is just a list of each object instance of the variable that it's needed. And these variables have properties. So if we go into our COBOL variable module, that is the dependency here, we can see I created a COBOL variable class, and it has all of these different properties. Most notably length. Not exactly sure what happened here, so we'll go ahead and undo that. We have our length, we have our name, our data type, all the things. Okay, after that, we have to allocate the memory itself. This is, during this function here, is where we go through and we do our calculation for the lengths of variables that are not explicitly defined with a length because they have children. And we also basically create the long string of memory that's needed for all the variables if they were to be lined up one after the other. And you can see that returns a tuple. The first element of the tuple is the list of variables, so any changes that have happened. So this originally goes in as length 0. Once it goes to the allocate memory, it'll come out length 11. And then also the memory itself, like I said, the giant string representing the memory is in element 1. This is a special set of variables. Don't really worry about this for right now. I'll get into that later. But this is like COBOL available variables, like system type variables. So these are added automatically. You don't have to specify them in your program here because they're system wide, so to speak. That's basically it for the initialization of the variables in the working storage or linkage section. Once we come out of that and we get into our procedure division right here, so this main represents the procedure division, we can see that we are setting the value of the variable using the set variable. We pass in the name, the value that we want to set, and this is the parent. So since it's itself, you send in the parent itself as the parent. Because there is, during the set, there is some recursion that could possibly happen depending on your variable and and the data that you're sending in. So as we can see over here, we want to move the literal hello world into the variable hello world, and that's what this is doing right here. You'll notice that we are taking, again, this returns a tuple, so we're taking element 1 of the tuple, and we're setting it to the variable representing the memory that was created up here. The reason for that is because we have just changed a portion of that memory, a slice within that memory. So we'll just go ahead and reset. You can see we pass it in, and then it gets sent back out. And then this is the list of all the variables that are available. So you can see here that the main list of variables contains all the variables in our data division and then our special system variables. There's also some other variables that are system variables for internal and then special register memory. Again, these are COBOL specific system variables for return code of the whole program. And then if you are to do sorting routines, sort return is a variable available for inspection after you do some sorting. So anyway, we'll get into that later also. So we basically have 4 types of variables that we are keeping track of: internal, special register, data division, and the EIB. And each one of those lists shares or has a memory set aside for it. And all the variables within that list share the same memory, so to speak. The other thing I want to mention here is Python does not allow dashes within variable names. You could have underscores. So I was thinking, you know, why would I have a function where I would pass in the name of the variable? Why wouldn't I just pass in the variable itself? You know, maybe I could convert dashes to underscores during the the conversion time. And I think I went down that route at the beginning, and it just, I don't know, it just didn't work out the way I was hoping. So I just quickly changed and said, I'll pass in the name, and then I can evaluate the list of variables, matching on the name, and then I know which element in this list I'm working with, because that represents the variable itself. The display variable is basically the display variable function is basically two functions. It is a get, and it is a print. So we can display literals, and in this case, the word literal is passed in because we want this to be whatever. This is not a variable name, this is a literal, so we want to print that out. Or we would pass in the variable name and the parent. And again, this is since it has no parent, it is its own parent. After a display statement, I insert a display empty string as a literal, and that is representing the carriage return line feed that happens. The reason for this is because this is a valid display command. So we could say display hs1 space hs2 space hello space ws1 space ws2. This is valid. So because of this, when I was doing the conversion, when is the end of the display statement? Well, it's when you either hit a period like this, or if you hit the next valid verb. So in this case, the next valid verb is stop run. But we could also, display done. Okay, so once I see this verb display, I assume everything after it is something to be displayed until I hit the next valid verb, which in this case is now another display, or a period, whichever comes first, because periods are optional in COBOL to a certain extent. You need at least one period per paragraph, and we can talk about paragraphs maybe some other day, but we could remove all the periods up to the stop run. This is a valid COBOL. We could remove this one. We'd have to put it back. This is valid. This is valid COBOL syntax. No periods here, and then just a period sitting all by itself. Let's see if this converts properly. So we do that. That's done. We go look at this, and you can see we have added in our new display here. This is the long line of these. So even though these are just calling the display for each one of these variables, no line feed is inserted until it is the literal with an empty string. So I've overridden the Python print statement to say don't put in a line feed. And then the true false at the end. I honestly, I don't remember what that is. So we can go to the definition here. Is it a literal, and is it the last in the line? And as you can see here, for literals, it's like it says yes, and then it's also the last in the line. So, and this one is yes, it's a literal, and no, it is not the last one in line. So you can see that that's how I'm manipulating the print statements based on the availability of the COBOL syntax to do things like this. So if we were to run this, we should see hello world from reading hello world, and then we should also see hello world from the concatenation of all of these individual variables. So let's go ahead and run it, see what happens. Right, so it says we expected hello world, we got hello world, this is the original. Then we printed hello world again, but this was individually using all these different variables, and then we printed the word done as a literal, and that's right here. Just in case you didn't believe me, I will change this to WS1, WS2, and then HS1, HS2. That will print world hello. We converted it. We can run our strike, or like I did last time, as I went to the Python and I clicked the debug. But this time I'll run strike, and we'll say it's hello world 03. Run that. Oops, it's not a 0, it is a capital O. And you can see this has been changed to world hello. So that's how that works. But what I am going to do is go back to the go back over here, and I'm going to put a breakpoint in here because I want to show you what the memory looks like. Actually, I'm going to put a breakpoint here. So we'll go ahead and debug, and when I hover over this, you can see we've allocated out 11 bytes, and it's empty at this point. Just to show you what this is, go ahead and get into the debug window down here. So you can see that's an empty string, and just to show you, we'll do a length of that. It's 11 because these all add up to 11. So we have that right there. All right, we'll continue on. So it's empty. Then we'll continue on. After we have set the variable, we'll look at it again. And you can see it has the value of hello world. If we wanted to, we could, and I'll just do this in the quick debug window, and then we'll call it a day on this. But let's say we wanted to do HS1, and instead of HE, is it 3? Yeah, instead of HEL, we're going to put in 1, 2, 3. And we'll go ahead and run that. And then we'll look at this, and you can see it's 1, 2, 3. Uh-oh. Something didn't work the way it was supposed to. There you go, guys. Live coding. This is what it's all about, right? Let's set this back here. Reset this. Okay, I think I know what it is. For the initial entry into the change, we want to match the variable to itself as a parent. Now we'll look at this, and we can see 123 LO space world. Yeah, so the first time we go in, we want to make sure that we match the variable name and also send itself in as a parent. And I forget the exact reason why, because obviously I made a mistake up here with this one. But I forget the reason why, but it is important, so we're going to leave it at that. And then if we just continue on here, we're going to see, oops, I botched that one up. All right, let's try this one more time. I clicked the debug button instead of the continue button. Again, live coding, guys. This is what it's all about. So we do this, we're here. We want to change that to 123, and then we will continue on. And you can see here it says hello world, hello world, expected hello world. We got 123 LO world, and then reversed world 123 LO. So that's how memory is manipulated in once it's converted to Python. I wanted to show you guys that. Thanks for hanging with me today. Remember, this is me by myself, making decisions, doing things. Is it the best way to do it? Probably not. Could the code be better? 100% yes. If you want to contribute to the repo, I would appreciate it. Remember, it's on GitHub, VIPER MF. We want the funk. That's my handle. All contributions are welcome. You know, put a pull request. Let's see what happens. But this is coming along. I'm pretty excited about this project. Again, improve the quality of life of developers. Make the feedback loop faster. Don't have competing resources like on a mainframe. Pull it down to the PC so you can use your own resources to get that initial coding done. Then you can push it to the mainframe and do your continuous integration and run it on the actual system that's going to be running it, just to verify, obviously, that it's going to work, and we can send it to production. So thanks for hanging with me. Give me a like, give me a subscribe, and I will see you next time.